Liftoff of Discovery.
Throughout the ages, humanity has been driven to extend its frontiers. This century, we have reached into the very depths of space. But the Space Shuttle Discovery's mission is to go barely beyond the boundaries of the planet. To look back at a frontier that has been one of our most ignored. The stratosphere, that thin veil of atmosphere above our heads that encloses and protects life on Earth. In the last 10 years, major attention has focused on the stratosphere above the most remote point on the planet, the frozen continent of Antarctica. On the ice, a small group of scientists waits out the long polar night, waiting for a drama about to unfold above them. Come the spring, high above Antarctica, unseen chemical reactions will carve a giant hole in the Earth's protective stratosphere, a phenomenon we have come to know as the ozone hole. Why it happens and what role we play in the drama has become one of the most disturbing mysteries of the 20th century. These people are part of the quest to unravel the mystery of the stratosphere, the mystery of what may be the most extensive human-induced environmental change ever recorded. Change that's spreading across our sky like a cancer. Our search for the answer to the Antarctic ozone mystery begins 3,500 kilometers to the north in the New Zealand city of Christchurch. For almost 100 years, the city has been a departure point for expeditions to the ice. It's now home to Italian, New Zealand, and United States Antarctic programs. As spring approaches, the scientists from the three countries prepare to follow in the footsteps of those first polar explorers. They'll face some of the harshest conditions on Earth. But because ozone depletion of the Antarctic continent is so dramatic, the region so untouched, it's the perfect laboratory in which to study the forces of environmental change. New Zealand atmospheric scientist Sylvia Nicol has been to the ice 5 times before. With her is Italian Dr. Carlo Valenti, another Antarctic veteran.
The ozone hole only occurs over the Antarctic, and there's a very good reason for that. The cold temperatures of the Antarctic allow a certain type of chemistry that depletes ozone to occur.
The scientists are about to come face to face with one of the greatest challenges to the future of life on this planet, unraveling the secret of the ozone hole.
Looks like a high and a low, don't it?
The story of ozone is the story of oxygen, the gas that keeps us alive. Almost 1/4 of the planet's air is oxygen, which sometimes reacts with itself to form ozone. Ozone molecules have 3 atoms, whereas breathable oxygen has 2. The total amount in the atmosphere is small, but 90% of ozone is concentrated in the stratosphere, between 10 and 50 kilometers above the Earth. It's this layer that absorbs the sun's most powerful radiation and prevents it from reaching the Earth. Before the ozone layer formed, the Earth was barren, unbearably scorched by the unfiltered rays of the sun. But within the protected depths of the ocean, early life forms began a process which is at the heart of all other life, the process of photosynthesis. Photosynthesis uses the sun's energy to break down carbon dioxide gas, making carbon available as starch, and the 2 oxygen atom molecule is released as a byproduct. Over billions of years, tiny bubbles of oxygen given off by photosynthesis found their way to the surface and began to gather in the Earth's young atmosphere, the first stages of the protective shield that filters out the sun's harshest rays. The sun's light reaches the Earth in a range of waves of different frequency, or wavelength, called a spectrum. We see only a small part of the spectrum, just the familiar colors of the rainbow. At the red end of the visible spectrum, invisible long wavelength light, we know as infrared, gives us the heat we need to survive. At the violet end is another range of invisible light with much shorter wavelengths, known as ultraviolet or UV. Life on Earth uses the UVA, which is closest to the violet end of the visible rainbow. But as the wavelength shortens, the light becomes higher in energy. UVB and UVC are both dangerous to living things. And that's where ozone plays its part. As oxygen drifts high into the stratosphere, it is struck by high-energy UVC light and reacts chemically. Oxygen molecules break into free-ranging atoms, and high-energy UV light is absorbed in the process. The freed atoms then combine with remaining oxygen to form the 3-atom molecules known as ozone. Lower-energy UVB radiation doesn't react with oxygen. It does, however, react with a more volatile ozone, splitting it back into free atoms and oxygen. The ozone quickly reforms, and so it goes on in a continual cycle, from oxygen to ozone and back again. A cycle that soaks up the sun's most damaging radiation, turning it into heat, and leaving the harmless longer wavelength UVA to pass through to the Earth's surface. So the ozone layer became the planet's radiation shield. And over billions of years, life was able to emerge from the primordial soup and flourish on the surface. Little was known of the role of the ozone layer until earlier this century. Ozone gas was discovered in 1849, but no one was sure of its role. For a time, people linked it to the smell of the seaside and considered it a supercharged form of oxygen. It became fashionable to holiday at coastal resorts and partake liberally of the ozone-laden air. In reality, a futile indulgence, as very little ozone occurs at sea level. And if it did, its volatility would cause lung and immune system damage. Only in the 1920s did British scientist Gordon Dobson confirm the existence and role of the ozone layer. But Dobson's work was overshadowed by another development about the same time by American industrial chemist Thomas Midgley Jr. Having discovered the benefits of adding lead to petrol, Midgley turned his attention to refrigeration, which then depended on pungent and poisonous substances like ammonia. Midgley developed a new group of compounds called chlorofluorocarbons, or CFCs, a synthetic chlorine gas that was cheap to produce and neither toxic nor flammable. CFCs opened the way to mass production of refrigerators, air conditioning units, aerosol cans, and polystyrene, and revolutionized modern life.
Our hospitals, of course, are continually aware of the danger of deadly microbes. And today, refrigeration has revolutionized hospital procedures and added years to the expectancy of life. In the meantime, little Mrs. Antifreeze has seen the light.
The world embraced its new perfect compound, the wonderful new inert gas that reacted with nothing else, or so it was thought.
And protected from contamination. Drinks cool and refreshing. All through the magic of the mountain.
As early as the 1970s, there were suspicions that CFCs may be linked to a slow decline in the thickness of the ozone layer. A decline scientists predicted would be noticeable by the middle of next century. But there was worse to come. And it would come from an isolated British base in the planet's most remote region, forcing a radical rethink of the science of CFCs. Ozone levels over Britain's Halley Bay Antarctic Research Station had been routinely monitored since the 1950s. Until the mid-70s, they showed a pattern of minor decline each spring, before increasing again through summer. Then in 1985, this man, Joe Farman, reported that ozone levels had begun to fluctuate wildly, at times reducing the spring ozone layer over Antarctica to almost half its normal thickness. It sparked international alarm and introduced a concept that would begin to alter the way we live, a concept we now know as the ozone hole. World attention suddenly turned to our most ignored frontier, the sky above our heads. But was the Antarctic ozone hole merely a sudden natural phenomenon, or evidence of humanity's growing impact on the atmosphere? 1987, and the search for answers was underway. From a remote airfield in southern Chile, a Lockheed ER-2, a civilian version of an American high-altitude spy plane, was put into the air on a special mission. The objective, to fly over Antarctica at twice the height of normal commercial airliners and take direct measurements from within the ozone hole as it developed. Flying at the very edge of space, the ER-2 confirmed massive concentrations of chlorine monoxide, a gas that increased in direct proportion to the disappearance of ozone.
I think the evidence is quite undeniable, and there is a component of dynamic transport that can affect the severity of the ozone hole, but the depletion of ozone is quite out and out a chemical effect caused by chlorine.
Argument began over the source of the chlorine. Antarctica's Mount Erebus lies directly under the ozone hole, but monitoring suggests its gases don't reach the stratosphere. The sea is another vast source of chlorine, but again, there's nothing to link it to sudden ozone destruction. Only one chlorine source was increasing at a rate close to the increasing chlorine levels in the stratosphere: the synthetic wonder compound chlorofluorocarbon. The theory went like this. At ground level, CFCs form one of the most inert gases known. There appeared little cause to worry if a harmless gas leaked into the environment. But while CFCs are extremely stable, ultimately that in itself becomes the problem. Once released, CFCs drift in the Earth's lower atmosphere for 30, perhaps even 50 years. If they stayed there forever, perhaps that's where the story would end. But near the equator, there's a gate in our weather system, a narrow band where air mixes into the upper atmosphere, carrying CFCs high into the stratosphere, where they're subjected for the first time to high-energy ultraviolet light. UV splits the CFC, releasing chlorine, and suddenly the ozone layer is under attack. The chlorine reacts hungrily with ozone to form chlorine monoxide and oxygen. Free oxygen atoms then react with the chlorine monoxide to reform oxygen gas, freeing the chlorine to attack more ozone. And so the destruction goes on until the chlorine encounters hydrogen or nitrogen and is locked into stable compounds. It's estimated the chlorine will have destroyed hundreds of times its own weight of ozone until there's not enough left to prevent the most damaging UV light reaching the Earth's surface. But why should the worst ozone depletion show up so far from the center of industrial production? And why so suddenly in the Antarctic spring? There was only one way to find out. For 4 months in winter, the Antarctic continent is in darkness, locked away from the rest of the world. Only by waiting out the polar night will the answer to the ozone riddle be found.
If you only come here in the summer, you would totally miss the event. So it is very important to be here year-round to completely understand the reasons and the development of this atmospheric cancer.
The scientific team at New Zealand's Scott Base have begun monitoring winter ozone levels. Peter Clark is one of the handful of scientists who've remained here throughout the long night. He's been taking continuous measurements using the light from the moon. The levels of moonlight indicate the amount of ozone it's passing through before reaching the ice. The study will help establish exactly when ozone depletion starts and how rapidly it develops. The most perplexing mystery in the ozone story is why the hole occurs only over Antarctica and only in spring. Part of the answer appears to lie in the giant whirlpool of wind around the Antarctic continent, known as the polar vortex. As the continent is plunged into darkness, temperatures plummet and the vortex intensifies. Chlorine and ozone-rich air drawn into the whirlpool is trapped over the southern continent. But why ozone destruction should happen so suddenly in spring was less obvious. Some sort of a catalyst had to be involved, and attention focused on the critical time of the Antarctic sunrise. As it draws close, spectacular clouds gild the sky, clouds which form only in the supercold polar stratosphere.
We first asked the questions, well, what's unique about this place? And it's that it stays dark for a long time. It's the coldest place on Earth, and the stratosphere achieves the lowest temperatures that you'll find in the stratosphere here during the wintertime.
American Joseph Smith has been studying chemical reactions within the polar stratospheric clouds.
When it gets cold enough in the stratosphere, ice crystals, and the stratosphere is normally very dry, I might add, ice crystals will begin to form if the temperature gets low enough. And those ice crystals allow some reactions to happen in the atmosphere that don't otherwise happen.
The compounds that previously locked up chlorine now react on the surface of ice crystals to release chlorine gas. The stratosphere becomes a primed bomb, waiting for the sun's return to split up the chlorine and unleash an unrestrained attack on ozone.
When a reaction takes place on the ice crystal, the chlorine is made free, and so it can destroy ozone if there's one last ingredient, and that is sunlight. So we have a cold stratosphere with ice crystals in it, eventually manages to release chlorine, and then along comes the springtime, the return of the sun, and this perturbed chemistry then, interacting with the sunlight, causes ozone to be depleted.
The sudden discovery and growth of the ozone hole caught the scientific community off guard. It pointed out how very little was known about the sky above us and forced a new approach to atmospheric study.
We brought in teams to study the physics, the chemistry of the ozone hole. So these experiments together in McMurdo with the satellite measurements that were made from space give us a complete picture, three-dimensional picture of the ozone hole.
The new combined approach would seek to overcome earlier oversights. Monitoring of global ozone levels had previously centered on America's Nimbus 7 satellite, which read UV light reflected by ozone in the stratosphere. But early signs of the ozone hole went unnoticed because scientists assumed that very low readings from the satellite were simply wrong, and it was left for ground-based scientists in the Antarctic to raise the alarm. Late August. The sun is just up, and the monitoring of the ozone hole begins in earnest with ground-based spectrophotometer readings. They'll build a reverse image of that provided by the satellite.
During the winter, we made our measurements with the moon, but now that the sun is up, we make measurements every day using the sun. In fact, we're actually measuring ultraviolet radiation. So the less ozone that's up there, then the more UV we actually measure coming through the atmosphere.
On each of the 7 trips Nicole has made, she's recorded ever lower ozone levels.
The lowest we've measured was 144 Dobson units, which is about half the ozone that we would expect to find if there wasn't an ozone hole. A few other stations on the Antarctic continent measured down to 110 Dobson units, and that's very, very low.
Spectrophotometer readings provide the baseline for ozone research, linking past results with current readings to allow accurate forecasts of trends and implications.
Well, the big question is whether what we're observing down here in the Antarctic, with half the ozone disappearing, whether that's in fact a precursor for what can happen at lower latitudes at places such as New Zealand.
But if ozone depletion doesn't spread to populated temperate regions, increased ultraviolet light falling on Antarctica alone could have dire results.
And so the depletion is very dangerous not only for us, but for all the life in Antarctica, because it's possible that the ultraviolet light makes some damage to the animals that live in Antarctica, like the seals, the penguins, the skuas, and the fish inside of the sea.
At Cape Evans, a Greenpeace team has been measuring sea ice depth and temperature throughout the winter. Led by Dr. Sabine Schmidt, this work will help to detect early signs that increased ultraviolet light affects phytoplankton, the base of the Antarctic food chain.
The Antarctic Ocean is the most productive ocean in the world and makes up perhaps maybe 10 or even 20% of the primary production of the world ocean. So if there is a drop in the production here, it would affect the oceans in the whole world.
Monitoring of the ozone layer now spans almost 4 decades. Measuring the effects of ozone thinning has only just begun.
155 centimeters.
Ah, right. Last time was 150, now it's 55. Yeah, 5 centimeters more.
Research like this is now crucial to establishing how much harmful UV light passes through the sea ice. Phytoplankton, microscopic algae, grows on the underside of the ice. Algae are the pastures of the Antarctic. They're the feeding grounds for zooplankton and ultimately for all other animal life in the Antarctic Ocean.
UVB is a very short wavelength ultraviolet which actually damages living organisms. And so the concern is really whether the UVB, which is increasing, whether that will cause damage to the algae. The repercussions will be that there'll be less algae growing there, and every year the ice breaks up and carries the algae out into the sea, the southern seas where many of the fish, whales and so on live, and they will have less food to eat. So if there's a serious effect and the algae die, then this will carry through onto the other animals and the fish in that region.
Out on McMurdo Sound, a New Zealand team collects samples of the phytoplankton by drilling the sea ice. Wrapped in black cloth to prevent contamination from sunlight, the samples are then taken back to the laboratory and tested under varying levels of UV light. Experiments like these may give some gauge of the future response of the phytoplankton and all other life forms to a future with a reduced sunscreen. The results of the test so far are encouraging.
If the increase in the ultraviolet, something like a factor of 2, really does hurt the algae, then it would be a very serious problem. Our studies have shown that even a doubling of the ultraviolet does not seem to hurt the algae substantially. It makes a small effect on them, but not a large effect. And so at this stage, I think we would be fairly optimistic that there'll be no serious repercussions as a result of the ozone hole.
By early September, the Antarctic's day is lengthening. The US base at McMurdo, the largest on the frozen continent, is now home to another phase of the ozone study to confirm the ground-based estimates of ozone destruction using direct sampling by balloons.
This is the time of the year when it's as early as we can get into McMurdo without staying throughout the winter, and therefore the temperatures in the stratosphere are really as cold as we're able to sample at this time. So we can sample the stratosphere and the ozone as it is in what we consider more or less its normal state, and then we can watch the progression as the ozone is being destroyed by chlorine.
Looks like it might be a little breezy. Okay, go ahead all the way.
But launching balloons can be a challenge in the volatile Antarctic environment. The partially inflated balloon will gradually fill itself as the air pressure drops at higher altitudes. Eventually, it will carry its instruments high enough to take direct measurements of gases at various layers of the stratosphere.
We measure ozone and temperature, so we get a vertical profile, and we try and do that every 2 days so that we get a vertical and a temporal history of the ozone as it's being destroyed over McMurdo in the springtime.
By October, the Antarctic night has shrunk to just 2 hours. The job of this Italian team now becomes critical.
No, credo che basta. Gli piacerà sto poco.
They'll use the final remnants of the polar night to unravel further the mystery of the polar stratospheric clouds. To confirm the cloud's central role in the ozone drama, they'll work through the short remaining darkness, firing laser beams into the stratosphere. The light reflected back to Earth will reveal what is hidden overhead.
When light passes through the atmosphere, part of it is reflected by the particles present there. We use this reflected light to monitor the atmosphere, and to detect this light we use a telescope.
The probe gives a profile of the height and density of the clouds. The profile matches changes in ozone levels detected by balloon sampling, confirming that stratospheric clouds and severe ozone depletion go hand in hand. just when it appeared the puzzle was solved, nature intervened. Mount Pinatubo erupted. One of the largest eruptions of the century, it threw huge amounts of volcanic debris up to 20 kilometers into the atmosphere, almost directly into the stratospheric gate over the equator. In the following months, sulfuric acid droplets from the eruption are carried around the globe. And in the next Antarctic spring, the Italians make a startling discovery. Acid droplets from Pinatubo have added to the polar stratospheric clouds. Their combined effects on the ozone could be devastating. After Pinatubo, nothing will be the same. Just weeks after the scientific team has departed, New Zealand takes on its own Antarctic appearance. Debris from Pinatubo has blocked the sun, exaggerating the El Niño weather pattern and bringing the worst spring snowstorms on record. Early summer, and on a plateau midway between the pole and the equator, another search is underway.
Probably over in the next fold, do you reckon?
Brian, the best we can do is just right straight up the valley.
Straight up that valley.
It's not a real strong signal, but it's a good sign.
Here in the heart of New Zealand's South Island, members of a balloon sampling program attempt to track down a prize. Thousands of dollars worth of precious monitoring equipment back from a trip to the stratosphere.
It's landing. Looks like the ozone pump is still good. Photo tubes are good.
The plateau at Lauder has long been a site of atmospheric studies. Pinatubo's legacy has been felt here too. Mature trees killed off by midwinter temperatures that plummeted to minus 20 degrees Celsius and below.
Just a gathered hole. Yeah. That's the one Terry and I reckon didn't open over in Karuna.
American Dr. David Hoffman has studied volcanic effects in the upper atmosphere since 1972. Here, he's using particle counters attached to balloons to check for sulfuric acid in the stratosphere. Results from these launches will be compared with those at McMurdo to broaden our understanding of stratospheric mechanics.
In 1992, we were expecting some major differences in the ozone hole because of the eruption of Mount Pinatubo. But some people back in the U.S. had done the laboratory measurements already, which suggested that volcanic clouds could be almost as important as the standard stratospheric clouds that form in polar regions. So we were expecting severe depletion, and we saw it. We really did.
It's sure, just check, Dave. It's surely, to me, going to the right.
Okay, on three. 1, 2, 3. Look out.
Real fine.
Pinatubo eruption will help us because it's like doing an experiment where you inject something into the system and then you look at what happens. And if the models are right, we should be able to predict what's going to happen. And so far, they're pretty good. We predicted there would be additional ozone depletion in Antarctica this year, and we did observe it.
Lauder is now part of a worldwide network of atmospheric monitoring stations established since the ozone scare. The network spans the two polar regions, the temperate zones and the tropics, to build a global view of what's happening in the stratosphere. UV monitoring and tracking of trace gases in the atmosphere is now building a picture of a frontier far more complex and dynamic than ever imagined.
We've only gone up 8 kilometers and really haven't gotten into the main ozone layer. We've only got 36 Dobson units, but at the end of the flight, this will be like 350 or something like that.
The stratosphere does not belong to any one region. anything that's placed in the stratosphere anywhere in the world will eventually find its way everywhere else. So the stratosphere is truly an international global region, whereas in the lower atmosphere you can pollute it and it will clean itself out before it crosses an ocean. That is not true in the stratosphere. So, like an eruption of Pinatubo in the Philippines, it only took 6 months to a year for the stuff to spread around the globe. Similarly, CFCs released in the northern hemisphere, where most of them are released, eventually find their way to the southern hemisphere. And most of this happens in the stratosphere, where the transport across the equator is quite free, varies with season, but does occur.
The arrival of debris from Pinatubo dramatically confirmed the role of clouds over Antarctica. In the spring of 1992, ozone was all but eliminated at altitudes where the volcanic debris was drifting. It brought the biggest ozone hole on record.
But it must be seen in the perspective of global ozone loss, chlorine molecules reacting with ozone in a catalytic way and destroying it. That happens all over the world. It just happens that in Antarctica or over Antarctica, because of the special circumstances, it happens in a very sort of catastrophic way in the springtime, where almost half the ozone in the atmosphere is gone for more than a month.
By late November, the sun circles above the Antarctic horizon 24 hours a day. The sea ice surrounding the continent begins to break up as the air warms. The polar vortex that has been containing the ozone hole loses strength, and ozone-depleted air mixes with air from further afield.
The ozone hole breaks up sometime between the late spring and early summer, and when that happens, ozone-depleted air that has been within the ozone hole drifts away towards the equator.
Already, the breakup of the ozone hole is popularly seen as the scourge of countries surrounding Antarctica. New Zealand and parts of South America are widely supposed to be now frying under an ozone hole each summer. But the reality is very different.
What happens essentially, we believe, is that the so-called ozone hole is mixed with air from other latitudes, and so the end result is more ozone over Antarctica, but less at other latitudes, and this effect we call the dilution effect. The changes that we're talking about at mid-latitudes are of the order of 0.5% per year. So it's a relatively small change, but it is an important change. It's a change in the atmosphere which is being driven by man's activities. And that's one of the very important messages, I think, about, you know, ozone in the atmosphere and ozone research. That's what it's shown.
Ironically, the changes in the atmosphere have drawn people of the world together. We all face the prospect of an ozone layer reducing at a steady and perceptible rate. The question now is whether we can remedy it.
The atmosphere just can't deal with this chlorine. We've been putting it in for some decades from the CFCs.
Tom Clarkson headed New Zealand's team at the first International Ozone Summit at Montreal.
During the 1980s, it was building up at about 5% a year, and it's this great reservoir of chlorine in the atmosphere, which is now running at about 6 times the natural amount of chlorine that you'd expect up there, that is causing this ozone depletion.
And the depletion will continue, despite international conventions. It's predicted that if we stop all CFC use today, it'll still be the year 2020 before chlorine levels in the stratosphere reach their maximum. What effect that will have on life at ground level remains unknown. Like many populated regions, New Zealand is situated in the temperate latitudes. Persistent winds give its capital the clearest air of any city in the world, making it an ideal center for monitoring the possible effects of ozone depletion on humans.
These monitors only register the UV radiation from the sun that causes skin cancer and sunburn. We're interested to see whether ozone depletion is having an impact on UV levels over the long period. Just recently, I took 2 of my UV radiometers to Greece. We did comparative readings against the Greek levels versus the Wellington levels during late summer, and quite surprisingly, the levels in Wellington during summer on a cloudless day were probably 40 or 50% higher than at the same time of the year in Greece. And this is probably something to do with the clarity of the atmosphere in New Zealand. It's very, very much clearer, and this lets so much more ultraviolet radiation through.
It's estimated that for every 1% decrease in ozone, there's a 4% increase in human skin cancers.
I think people should be very conscious of the dangers of exposure to UV radiation. It can be very deceptive. We have no inbuilt sensor to tell us that we've got UV radiation, and I think a big danger right throughout New Zealand, in fact, is there's frequently a cooling breeze, so we can stay out in the sun an awful lot longer.
Pretty breezy out there. Watson bowling into it. And that's the end of the over. 112 for 2 after 27.
The basic message is that in the middle of the day there is a large amount of ultraviolet light which will burn the skin, and it's important therefore that the kids wear sun hats to protect particularly the ears and the back of the neck, because research shows that in later life people that were burnt, particularly while they were young, are more likely to get a skin cancer which is called melanoma, which can be fatal.
And in December, as the first scientists return from the ice, their new data suggests other worries.
Well, it's possible that the ozone holes could get even deeper if the depletion happened at other levels within the atmosphere. At the moment they're limited to the Antarctic, but it's possible that similar sort of things could happen, such as a volcanic eruption could allow those reactions to happen elsewhere.
Attention is particularly turning to the potential threats in the northern hemisphere.
Over the North Pole, they talk about the atmosphere being primed for ozone depletion. There's enough chlorine up there to destroy a lot of ozone, and so they're starting to become very concerned about the whole issue.
But the whirlpool of polar winds at the center of the present ozone hole is an Antarctic phenomenon.
This builds up to extremely high velocities in Antarctica, which it does not in the Arctic. And this is thought to be related to the land mass. There's a lot of land mass in the northern hemisphere, which causes disturbances in this vortex. So it never gets as uniform, it never gets as cold. If it doesn't get as cold, these clouds don't form as readily. If the clouds don't form, the chlorine doesn't get converted, and even though there's all kinds of chlorine there, just as much as here, just as much as Antarctica, it's in a form that doesn't destroy ozone.
In the Antarctic spring, we see 50% of the ozone disappearing. In the Arctic, we see between 5 and 10% depletion.
But recent satellite measurements indicate that Pinatubo has now pushed northern hemisphere depletion to 15% and beyond. And while industrialized nations have moved to cut down CFC production, there's already so much gas in the environment, the ozone story may have barely begun, and more has yet to be added. CFCs and other ozone-destroying chemicals are still used in refrigerators, as well as foams, solvents, fire extinguishers, and asthma inhalers. Officially, CFCs aren't due to be phased out until 1996, and in some areas, another 10 years after that. The refrigeration industry, which has been a major focus of pressure against CFC use, has moved some way towards using substitutes. Fridges using a chlorine-free hydrofluorocarbon are now being manufactured, but production of this alternative gas is more complex and expensive. And there's a potentially much larger problem still looming. Some nations, including China and India, haven't signed or are exempted from international treaties on CFC use. Since the late 1980s, the number of Chinese homes with a refrigerator has soared, adding millions of extra CFC-based fridges to the world total. The effects of this explosion have yet to be seen. Unless practical collecting or recycling systems for CFCs are put in place, the ozone hole will get worse before it gets better. But in spite of the weight of scientific attention, it's through the mass media that most people are learning of the immediate risks to them from increased ultraviolet levels.
21 degrees and cold on that floor. And you'll burn after 15 minutes of sunshine at the hottest time of the day if you have fair skin.
In the heart of the capital, it's 25 degrees, and if you're out there, be careful. Who's in beyond the weather monitors is condition extreme. Give me time, carry me up through the hole in the sky. Don't leave me alone with no home to go to, and the ozone's gone bye-bye.
While attention is focused on the personal risks of increased skin cancers, the long-term implications means the role of the pressure groups may be far from over.
What we're experiencing with ozone depletion now is based on the CFCs that went up into the atmosphere in the 70s. We can't afford to go on increasing our input of ozone-destroying chemicals at all.
We have had a love affair with CFCs for 50 years. Scientists now tell us the consequences could include a southern hemisphere ice age or even total atmospheric disruption. Whatever the outcome, the warnings are there for us to heed.
The awkward thing is, you know, people sometimes say to me, oh, you're just doing it for publicity. But as I said, I'm a father of 4 kids. And we all, anybody, kids and grown-ups alike, you know, heard about this thing a few years ago, which is this whacking great hole in the ozone layer. Now, the first thing I think we all thought was, don't worry, they'll ban these CFCs and they'll make all this legislation, we'll be all right, and maybe it'll close back up again, you know. I hope so. But that's not what's happened.
The ozone hole has been likened to a mild heart attack, a warning that globally we need to change our lifestyle, a warning that will continue to haunt us for a long time to come.
The amount of chlorine that is now in the stratosphere has committed us to an ozone hole down in the Antarctic each springtime for the next 100 years.
It's like, I've got to use some of this time to say, look, you know, any politicians watching or any people watching, I really agree with you, and I'm saying it for you, you know, that we want that hole closed, please.
In the end, the present ozone hole over the Antarctic may not in itself be catastrophic, but it is already regarded by scientists as so significant, its global effects will be still evident in 1,000 years' time. How significant remains to be seen. The effects of a seemingly innocuous refrigerant on the band of ozone high above the Earth's surface have at least disturbed our complacency over what happens beyond our immediate horizon. Our future may ultimately depend not on scientific attention to the atmosphere, so much as on the popular action that it provokes. History will tell whether the awakening has come in time.